Let's look now at section 9.7, talking about Taylor polynomials. In previous courses in Cal 1, we've seen that a curve can be approximated at a point using a linear equation. Essentially, we can say, okay, here's a curve that looks like this, and at this point, I can perfectly approximate it with a straight line, which you'll remember as the line that's tangent to the curve at that point. Right? So this line is not exactly the same as the curve, obviously, but it is a decent approximation near that point. As long as you're near this point, the curve and the line are really pretty close. All right? If you look at just things nearby, those things are really very close to each other. Now, of course, as you move away, that approximation gets worse and worse and worse. Okay, well, the reason for that is, of course, you have a straight line trying to approximate a curve. It gets even worse when you start having things that are, well, more complicated. For example, let's say I have this curve here. I'm going to have, let's just say I have a sine curve, sine function like this. And again, I can approximate this using straight lines. I can say, okay, at this point right here, I can approximate my curve using a straight line, the tangent line. All right. And of course, we can find that using the derivative. All right. Note that at this point, the derivative of this line, well, since that's a straight line, that's just its slope, and the derivative of this line are the same at that one point right there. So if I label this function f of x, and I take this function, I call it p of x. I'm going to say p for polynomial, because of course that's a linear equation. It is a polynomial. I'm going to call it p1, just to designate that as a polynomial of degree 1. What I can say about those two functions is that they are very different, but that at this point they are the same. And not only at this point are they the same, but also their first derivative is the same. All right. So here, note that at this point, and here let's call this let's just call this x naught. At x naught, f prime of x naught is the same as p1 prime of x naught. Well, sure, that's how you found that line in the first place. You found the slope of the tangent line by taking the derivative, and then using that slope, you form that line. Okay, but why does it have to be a line? After all, I have polynomials of degree 1. Why don't I use a polynomial of degree 2? After all, a polynomial of degree 2 would be, well, it would be a parabola. And the nice thing about a parabola is that it curves, it bends, which will give me a better approximation of my function. If you think back to Cal 1, the second derivative gives us, well, the first derivative, rather, gives us the slope of the tangent line, while the second derivative gives us the concavity, concave up or concave down. So if I can have another polynomial, and let me use a different color here, that passes through that point, yeah, I can have my function have the first derivative equal, but I can also have this function have the second derivative equal to. So here I can say at x naught, I have a function, and let me call this one, I'll call this one p2, again, just to designate the fact that it's a second order polynomial. It's a quadratic. And at this point, I can say that, well, I have f prime of x naught is equal to p2 prime of x naught. Because again, you'll notice right here, they both have the same tangent line. Notice both of the original function f and this parabolic function p2 both have the same tangent line there. But not only are their derivatives equal, but their second derivatives are equal too. Notice their curvature matches at that point, their concavity. So here that's f double prime of x naught is equal to p2 double prime of x naught. Oh, okay. So by having a higher order derivative, I have more, by having a higher order polynomial, I have more of their derivatives match. But visually, I can see that these match up a little closer because, of course, here, this only matches the derivative, the first derivative, the direction, whether it's increasing or decreasing. But this one matches not only whether it's increasing or decreasing, but also its concavity. Well, what if I had a third degree polynomial? If I use a third degree polynomial, I can approximate this function, with just a bit more precision. Here, instead of approximating with a line or a parabola, let me approximate it using a cubic polynomial. I'll call this one P3 of x, like this. And that is a third degree polynomial that approximates my function. But again, at that point, well, notice the derivatives are the same. They're both increasing in the same way. So here at x naught, I get f prime of x naught is equal to P3 prime of x naught. They're both increasing. Their first derivative behaves the same way. They're both concave down at that point, so their derivative behaves the same way. F double prime of x naught is equal to P3 double prime of x naught. But not only that, but now notice we have a third degree here, which means now not only do we have our same concavity, but all of a sudden we have the ability to detect an inflection. All right? So here we have the third derivative is equal to the third derivative of P3. And of course, I can keep going. I can approximate this with a first degree polynomial or a second or a third. If I now take a fourth degree polynomial equation, I notice that it follows my curve even longer. If I use a fifth degree, sixth degree, seventh degree, notice it will never follow the graph perfectly because, of course, my sine function oscillates forever and ever. It goes up and down and up and down. A polynomial only has a certain number of bends in it, so it will never follow it perfectly. But notice that the more degrees of a polynomial I have, the better approximation it is for longer. This leads us to what we call the Taylor polynomials, which are a generalization of the find the equation of the line tangent to the curve to generalize into higher degrees of polynomial, which will give us better accuracy. So let's take a look at that. And in fact, let's use this illustration for our very first example. We're not going to define it just yet. First of all, I want to show you guys how to set this up just a bit. Then we'll define it and formalize it. All right. So what I'm going to do is I'm going to say, let's go ahead and consider the function f of x equals, and let's keep things the same as we had above. Let's talk about the sine function, sine of x. Okay. So here, let's go ahead and take a polynomial, and I'm going to stop at a third degree. Let's find a third degree polynomial. In my case up here in my notation, I'm looking for P3. I'm looking for something of degree 3. Find a third degree polynomial function that approximates our function. In previous courses, we would have said the line that's tangent to the curve. But now, since it's not a straight line, the word tangent doesn't really make sense anymore. Tangent lines are straight lines here. Right? So here we want to say, okay, we want to find the line that, instead of saying tangent, we're going to say the line that approximates the function. And our function is f of x equals sine of x at the point 0, 0. All right? Here, I'm trying to approximate it at this point, not at this point or this point over here. So when we approximate, we have to approximate it at a particular point. That'll become a little bit more important later, but for now, let's just set things up as they are. Right, now, this first example, I'm going to do it slightly longer than the way you normally would. Normally, you would just jump directly to the third degree polynomial function. But here, I'm going to start from the lower degrees and build them up. This is going to do two things. One, it'll show you a few examples all in one, but two, it'll show you why that third degree polynomial looks the way it does. Okay, so now I'm going to start off with a 0 degree polynomial. So what's a 0 degree polynomial? That's a point. Because after all, if this function that I'm going to make, this polynomial function that I'm going to make, whatever it is, if it's going to approximate my curve at that point, well, then it better cross at that point. Otherwise, it's a terrible approximation. So if I have the polynomial of degree 0, then that's just going to be, oh, I just want to make sure that my point is the same as my function at that point. Okay, so here I just want to have, now notice I'm plugging in 0 right here. So that's just going to be a constant, a sub 0. All right, and that's going to be my function. Oh, let me space that out a little bit more. I'm going to have f of x equals a sub 0. Because after all, that's what a 0-degree polynomial is. It's a constant. Okay, so I want that function to be equal to my function. And here, let me say p. That way I don't mix it with that f. I'm going to say p0. And that's going to be f at 0. Okay, so here, this has to be the same as f. Oh yeah, but they don't have to be the same everywhere. I mean, obviously not every point is the same. We only care about it at a particular point. So here, if I want p of 0 of 0, and I'm getting that 0 from here because that's the x value I'm trying to plug in, then that's got to be the same as f of 0. Oh, but I know how to do that. That's going to be sine of 0, which is 0. Okay, that's nice. We get 0. Okay, no big deal. All right, now let's talk about degree 1. Well, that's going to be a linear equation. So here we want p1 of x is equal to a sub 0 plus a sub 1x, just like that. Well, notice that's just the slope of the tangent line, all right? Right here, the slope of the tangent line. Well, yeah. Look up here, though. We had, for any of these that we're building, what we want to do is we want to have the first derivative of f match the first derivative of our polynomial. And notice that's going to be true for any polynomial, whether it's degree 1, 2, or 3. Now, if you have higher degreed polynomials, you'll be able to look at higher derivatives. But they all start off with f prime equals to p1 prime. All right? Okay, so here, well, what does p1 prime look like? Well, let's see. If I take the derivative of this, I'm going to get, well, that's a constant, and its derivative is 0. Okay, and then the derivative of a number times x is just that number. Oh, okay. So if I take the derivative of p prime of p1 prime, if I take p1 prime, I'm going to get a sub 1. But notice a sub 1 is that coefficient right there. Oh yeah, but in order for this to be a good approximation, that p1 prime is supposed to just equal to f prime. But since p1 prime at x is supposed to be the same as f prime at x, well, then that just means that instead of saying p1 prime of x is equal to a1, we can just say f prime of x is equal to a1. That means f prime of x is equal to a1. Oh, but that's easy enough to do. I know how to plug that in because I know what f is. F is sine of x. So that means that a sub 1, that number right there, is going to equal to the derivative of f. Oh, well, the derivative of the sine function is the cosine function. And again, we're going to plug in the number 0, which is the number 1. Ah, okay. So then that means that p1 of x is equal to, well, we know that first number was 0 because we found it above. A sub 0 was 0. Plus, oh, now we know a1 is equal to the number 1. Okay, so it's going to be 0 plus 1x. Okay, so it's just 1x. Just like that. So this is a first degree polynomial function that approximates sine of x. Now here, this looks a little more complicated than what we've done in previous courses in Cal 1, but all this says is, okay, here's your sine function. Let's see. Here's your sine function, here's 0. And if I approximate it using a straight line, well, if that straight line is y equals to x, hey, that actually is a pretty good approximation of that, at least at this spot. But again, we can do better. So let's consider a polynomial approximation of degree 2 now. This is the polynomial approximation of degree 1. Let's take a look at a polynomial approximation of degree 2. Again, normally the problems aren't this long, but here I wanted to extend it to show you a few different examples using the same function, but also to show you where these numbers are coming from in the first place. So let's say I want to find now P2 of x, the second degree polynomial that approximates my function. Okay, well, P2 of x is equal to, and remember this is a quadratic, so this is going to be A0 plus A1x plus A2x squared, just like that. Okay, well, we need to find out what these numbers are. After all, these are just variables, right? This will be, something plus something x plus something x squared. So we just need to find the A0, the A1, and the A2. Well, again, A0 is just supposed to be the point where my function exists. I'm trying to find that one point where I'm trying to find the approximation of. So here, this a sub 0 should be nice and simple. It should just be what I get when I take the original function and plug in that initial point. In our problem, I'm plugging in 0. Okay, well now, we just saw a sub 1 is supposed to equal to f prime of x sub 1, of x sub 0. And that was the result that we got from the previous one. Right? Here we have that a sub 1 is equal to f prime. Okay, so a sub 1 is equal to f prime. All right, so it looks like I have a pattern. Maybe f sub 2 will equal to f double prime. Well, almost, but not quite. A sub 2 is equal to. All right, well, how do I find that? Well, remember, our approximation is such that f double prime is supposed to equal to p2 double prime. All right, well, there's p2. Let's find p2 double prime. If I take the derivative of this one, p2 prime, the derivative of a constant is 0, so that's gone. The derivative of a1x, well, that's the derivative of a constant times x, that's just that constant. And the derivative of a2x squared, well, I use the power rule. I take the 2, bring it down, subtract 1 from the power. So there's my derivative. But now let me take the second derivative, because that's the one I really need for this. Well, that's a constant, and the derivative of a constant is 0, so that's gone. And here that's a constant times x, x to the first power. And the derivative of a constant times x is just the constant. Oh, but again, we need p double prime to equal to f double prime. And it doesn't matter what degree of polynomial function we have. P double prime needs to equal to f double prime. Oh, okay. So then that means that, well, P double prime, that means that that's the same as saying f double prime of x is equal to 2a sub 2. Oh, but I don't want 2a sub 2. I just wanted a sub 2. Okay, go ahead and divide both sides by 2. So that's going to be 1/2 f double prime of x is equal to a sub 2. So notice it's not exactly the second derivative, but it's close. It's 1/2 times the second derivative. Okay, so right here, all I need to do is to find my coefficients. I can say, well, let's see, a sub 0 is equal to f, which is the sine function, and I'm going to plug in 0, because that's the point I'm trying to approximate at. I'm trying to approximate at 0, 0. A sub 1, well, that's going to be the first derivative of my function. Well, the first derivative of sine is cosine. And again, I'm plugging in x is equal to 0. And a sub 2 is supposed to equal to, well, the second derivative of sine, the derivative of cosine, would be negative sine of, and again, I'm plugging in 0 here. And again, the reason I'm using 0 is because my initial point was 0, 0. If this was a different point, well, I'd be plugging in a different number over here besides 0. Okay, well, now I know what all those numbers are. That's 0, that's 1, and that's 0. So that means that my P2, my second degree polynomial function that approximates the sine function, is, well, that's 0 plus 1x plus 0x squared. Which sounds a little strange. You're saying, oh, so then you're saying you shouldn't add an x squared term. Essentially, yeah. By adding an x squared term, we end up making our approximation a little bit worse. What do you mean by worse? we'll talk about that in a little while. We'll talk about convergence of these things. We're getting to that. So finally, let's take a look at answering our final results. Let's take a polynomial function of degree 3. Well, that's p sub 3 of x equals to a sub 0 plus a sub 1x plus a sub 2x squared plus a sub 3x to the third. Right? And we need to find out what a sub 0, 1, 2, and 3 are to get our third degree polynomial. Well, again, we already know some of those results. We know a sub 0 should be equal to f at x sub 0. We know a sub 1 should equal to f prime at x sub 1, at x sub 0, rather. We know a2, that coefficient there, should equal to 1/2 f double prime of x0. And now we're trying to find a sub 3. Notice that here, this is generic. This had nothing to do with this being the sine function. Right? Here, I'm deriving these results based off the idea that I'm trying to approximate a function. I'm never actually using that it's a sine function until I plug in at the end, which means that these will continue to be true for other kinds of functions. All right, so what is this? Well, again, if we take the third derivative of our third degree polynomial, that's supposed to match the third derivative of the function f. Okay, so if I find the third derivative of this, well, let's see here. P sub 3 prime of x is, well, the derivative of the derivative of a constant is 0. The derivative of a number times x is just that number. Okay, just like that, a sub 1. The derivative of this one, well, I can take the 2 to the front, subtract 1 from the power, like that. And then the derivative of this one, I take the 3 down to the front, subtract 1 from the power, and that gives me that. Okay, so now let me do that again, because after all, I don't want the first derivative. I want, well, it looks like the third derivative is what I'm looking for, yeah? So p sub 3 double prime of x. Okay, well, now that's a constant, even though it wasn't before. Now, after taking a derivative, it's a constant. And the derivative of a constant is 0, so that's going to go away. The derivative of a number times x is just that number. And now here I can use the power rule. Take the 2, bring it down. So that's going to be 3 times 2 times a sub 3x, like that. Now you say, well, 2 times 3 is 6, right? Absolutely it is. But I'm going to leave it like that just to show something in a little while. And now let me take the third derivative. P sub 3 triple prime of x. All right, well, my apologies. That was, there's not supposed to be an x there. The derivative of a constant times x is just that constant. Okay, so now I'm taking the derivative. That's a constant. And the derivative of a constant is 0. Okay, and now the derivative of this, well, this is the derivative of a number times x, which will just give me that number. So that's 3 times 2. Here I'm going to write it as 3 times 2 times 1, which doesn't change anything, right? 3 times 2 is the same as 3 times 2 times 1, times a sub 3. Here, that's a constant, and the derivative of a constant times x is just that constant. But we saw that in order for this to be a third degree polynomial approximation, the third derivative of that polynomial should be the same as the third derivative of our function. So here, that third derivative of our polynomial should be the same as the third derivative of our function. Oh, well, that's going to be 3 times 2 times 1, a sub 3. But again, I didn't want a 3 times 2 times 1 times a sub 3. I just wanted a sub 3. Okay, so here that's going to be divide both sides by this. So this will be 1 over 3 times 2 times 1, f triple prime of x. That's equal to a sub 3. Okay, so that's going to be 1 over 6 right here. 3 times 2 times 1 is 6. F triple prime of x naught. Notice something right here. 3 times 2 times 1. That's a factorial. That's going to become important here in just a minute. First, let's go ahead and finish off this problem. and then we'll talk about why that turns out to be very, very important. But finishing off this problem, we know that we want these to be our coefficients, a0, a1, a2, and a3. And we know we want this to happen at x equals to 0, all right, because we're at the point 0, 0. So our coefficients are, well, let's see, a sub 0 is equal to the original function at 0. Okay, so sine of 0. A sub 1 is the derivative of sine, which is cosine at 0. A sub 2 is 1/2 times the derivative of the derivative. Okay, the derivative of cosine is negative the sine of, and here, since we're substituting in 0, we'll plug in a 0 there. And a sub 3 is going to be, okay, take the derivative again. The derivative of this sine is, the derivative of negative sine would be negative cosine. But again, that's being multiplied by 1/6. So that's 1/6 times negative cosine. And again, that's at 0. And if I evaluate all of those, that's going to give me 0. That's going to give me 1. That's going to give me 0. And that's going to give me negative 1/6. And so the third degree polynomial function that approximates my sine function, p of x, is p sub 3 of x, because I'm looking for a specific one, is going to be given by, well, there's not going to be a constant, but there's going to be 1x, because that's the coefficient here, a1, so that's going to be 1x. There's not going to be an x squared, because that coefficient is 0. But then over here, that's going to be minus 1/6 x to the third. And there is a third degree polynomial function that approximates the sine function at 0, 0. Okay, so now this seemed very, very long, but the reason I made it long wasn't because the problems inherently have to be that long, but to try to get you to see this pattern. Notice that to take the first coefficient, you're just looking at the original function. This coefficient, you're looking at the first derivative. This coefficient, you're looking at the second derivative. This coefficient gives you, you're looking at the third derivative. So a sub 4 looks like it would come from f sub 4, fourth derivative of f. F sub 5 would come from the fifth derivative of f. Well, yeah, but not exactly, because look, these numbers here, there's these extra numbers. Well, yeah, but here we see that it's a factorial. Notice, if I start off with something that looks like a to the power n, let's say that's my function. If I take a derivative, I use the power rule. Oh, here, let me write that as x to the n. That's going to be n. Take the n, bring it down, subtract 1 from the power. Oh, but if I take another derivative, that's going to be n times n minus 1, because again, I brought that number down, times x to the n minus 2. If I do that again, that's going to give me n times n minus 1 times n minus 2 times x to the n minus 3. Notice, here I'm just starting from n and counting down. n minus 1, n minus 2, the next one will be n minus 3, until eventually, if I take the nth derivative of f, then I'm going to end up with n times n minus 1 times n minus 2 times n minus 3, dot, 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 all the way down till I get to 3, and then 2, and then 1. And then that very last one, this constant disappears on me. So here, that's going to give me n factorial. Just like this. So we saw that right here. We saw if we take the third derivative, we get 3 factorial that we're dividing by. If we took our second derivative, we were dividing by 2 factorial. After all, 2 factorial is the number 2. You say, well, what about up here? Well, here we took the first derivative, and we divided by 1 factorial. After all, 1 factorial is the number 1, so it didn't change it. So here, we can write these in a slightly different way. We can say, to approximate f of x with a polynomial, the coefficients will be a sub 0, a sub 1, a sub 2, a sub 3, a sub 4, and so forth and so on. Okay. From our previous example, or from our previous examples, we saw that that was f of x naught. We saw that was f prime of x naught. We saw that was 1/2 f double prime of x naught. And we saw that was 1/6 of f triple prime of x naught. Here, I'm going to leave that one blank for a second. I can rewrite this. There is a convention in mathematics. Here, I'm just going to go ahead and write this to the side here. Recall that by convention, 0 factorial is equal to 1. I'm not going to go into that. That's something from number theory. This is a convention in math. 0 factorial is equal to 1. So here, I could write this as 1 over 1 times f of x naught. I could write this as 1 over 1 f of x naught. Oh, sorry, f prime of x naught. I could write this as 1 over 2 f double prime of x naught. And I could write this as 1 over 6 f triple prime of x naught. But you know, since 0 factorial is equal to 1, I could write that as 0 factorial. So let me write this as 1 over 0 factorial, f of x naught. I can write this as 1 over 1 factorial, f of x naught, prime. I can write this one as 1 over 2 factorial, f double prime of x naught. And here, 6 we've seen as 3 factorial. That's 1 over 3 factorial of f double prime of x naught. So, following triple prime. Following that pattern, that suggests that this one should just be 1 over 4 prime of f quadruple prime of x naught. And the next one would be 1 over 5 factorial times the 5th derivative. The next one will be 1 over 6 factorial times the 6th derivative. And eventually, we would get down to the nth coefficient, which would be equal to 1 over n factorial times the nth derivative of f at x naught, or as it's often written, the nth factorial, the nth derivative of f at x naught over n factorial. This shows you the coefficients of your polynomials. Regardless of what your original function was, here notice we made no mention of any particular function, just a function f. This gives you the coefficients of the polynomial of any degree. Because here, since that's an arbitrary n, we could use any value. We use any degree for our function. So, this also shows you one other thing. Why we kept talking about factorials in previous sections. We were talking about evaluating factorials we were talking about simplifying series that involve factorials. That's what this involves. Notice, this is just a sum. We're adding together terms of a polynomial. The coefficients all involve a factorial. So all of a sudden we have a series, we have the sum of things which involve factorials. Let's take one more example, and let's keep this one a lot simpler, because here I already have everything I need. So here I'm going to go ahead and say example. Let's find the polynomial of degree, and let's just say degree 4, that approximates, let's say f of x equals e to the power of x, and again we'll do this at 0, 0. Oh, sorry, not 0, 0, that would be 0, 1. 0, 0, the graph of this doesn't pass through 0, 0. It would pass through 0, 1. Okay, so let's say we have that. Here what I want is I want p sub 4 of x, which is a polynomial function with degree 4. So that's going to be a sub 0 plus a sub 1x plus a sub 2x squared plus a sub 3x to the third plus a sub 4x to the fourth, since we're looking for a fourth degree polynomial. Now, in the previous problems, we saw that it takes a lot of effort to start deriving and evaluating. But all of that effort brought us to this conclusion, which means that now I can just use that conclusion for any function. So here a sub 0 will be 1 over 0 factorial times the 0th derivative. You say, what's the 0th derivative? That means don't take a derivative. Okay, so just like that. The first coefficient, a sub 1, is going to be 1 over 1 factorial times the first derivative. A sub 2 will be 1 over 2 factorial times the second derivative. A sub 3 is 1 over 3 factorial times the third derivative. And a sub 4 is equal to 1 over 4 factorial times the fourth derivative. Just like that. But we know that our function, f of x, is e to the x. And the nice thing about e to the x is it's always its own derivative, right? So here that's going to be, well, let's see, that's 1 over 1 times, take your function and plug in 0. So that's e to the 0. Here, that's 1 over 1. The derivative of f is still e to the x. And again, I'm going to plug in 0. Notice here, that's the function, that's the derivative. It just so happens that e to the x is its own derivative. Here, that's 1 over 2 factorial is 2. And again, the derivative is still e to the x, which we're plugging in 0 into. Here, that's going to be 1 over 6. And again, the derivative is e to the 0, or is e to the x, which we plug in 0 into. And finally, 1 over 4 factorial, that's 1 over 24. And again, the derivative of this would be e to the x again, which we're going to plug in 0 into. So here our coefficients are 1, 1, 1/2, 1/6, and 1/24. So in the end, our p sub 4 of x, our fourth degree polynomial that approximates e to the x, is equal to a sub 0 plus, let me just write in the numbers themselves. We know what our a sub 0 is, so it's going to equal to 1 plus 1x plus 1/2 x squared plus 1/6 x to the third plus 1 over 24 x to the power of 4. Just like that. Incidentally, this is all calculators and computers can do. You ever notice you punch something into a calculator and you get an approximation? Well, of course you get an approximation. After a little while, your calculator runs out of spaces, right? After a while, you run out of spaces here. There's only so many spaces you can type into a calculator. And likewise, there's only so many spaces that your calculator can write out for you. Your calculator and computer use this to an advantage. Calculators and computers don't actually compute e to the x. What they do is they take a polynomial that has 2 or 3 or 4 or 5 terms, whatever is necessary to get you to that many digits, and instead of I want e to the power 0.5. Instead of plugging in 0.5 into here, they plug 0.5 into here. Because after all, these are approximations of this. So as long as I'm not very far away from 0, if I'm trying to plug in something like 0.5, if I plug it in here, or if I plug it in here, the answers are going to be super, super close. And in fact, they're going to be so close that your calculator would run out of digits before you saw the difference. In real life, e to the 0.5 and this polynomial with 0.5 plugged into it, they do have a difference between them. There's a difference between the digits, but those would come way after this. The digits would come way over here when you first see the difference. That's how calculators and computers are set up. They don't ever do math with exponentials. Same thing for logarithms. And in fact, same thing for sine and cosine. Calculators and computers don't work with sines and cosines, exponentials, logarithms, arc functions, or anything else. Computers and calculators run exclusively with polynomials because polynomials are good enough to approximate this. So now let's take a look at a formal definition of all of this stuff. This won't be anything new, but it formally summarizes everything we've seen so far. Let f of x be an nth differentiable function at c. That might be a new phrase for you, an nth differentiable function. A differentiable function means you can find f prime. A twice differentiable function means you can find double f prime, right? The second derivative. A third differentiable function is something where you can find f triple prime. An nth differentiable function just means you could find n derivatives. First derivative, second derivative, third derivative, fourth derivative, all the way up to n, the nth derivative. Here, we want it to be n differentiable at c. That means that we're looking for a derivative at a particular point. We're going to plug something into that derivative. Okay? So if you have f of x is an nth differentiable function, you can find n derivatives. At c, you could plug in c into all of those derivatives. Then p sub n of x, which is the notation that we were using before, is equal to this polynomial right here. It's f at c, so you're taking the function and plugging in c. You're taking the function and plugging in c, plus f prime of c over 1 factorial times x minus c to the first power, plus f double prime at c over 2 factorial times x minus c to the second power, plus dot, 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 all the way till you get to plus the nth derivative of f at c over n factorial times x minus c to the power n. This is called the nth Taylor polynomial of f at c. Now, the two examples that we saw, we plugged in the number 0. It doesn't have to be the number 0. You can use a Taylor polynomial anywhere along the function. But the first examples we ever see are with 0 because they numerically are just a little bit nicer. There's a special name for those. If you have, this is a Taylor polynomial of degree n at c. If you specify specifically at 0, notice all these c's reduce down to zeros, and x minus c reduces to x. X minus c squared reduces to x squared. The c is 0. If all of your c's are equal to 0, that's also called the Maclaurin polynomial of f. These are two different mathematicians. Maclaurin did his work with this kind of polynomial specifically at 0, and then Taylor went through and expanded on his work to give us something a little more general. This only works at 0, whereas this works at any point along your function. So we've seen two examples already of the Maclaurin polynomial. The first one was the one that was very somewhat long and drawn out, that I started with the sine of x over here, and I went through degree 0, degree 1, degree 2, and degree 3. But those are substantially longer than their problem ever really needs to be. Here, I was developing the notation, and I was developing why each of these symbols is the way they are. This problem that we saw using e to the x, that one is more or less what these problems look like. You have your function, you find the coefficients, and then put together your polynomial. Notice here I've relabeled this a bit. In the previous time we saw this example, we said find the polynomial of degree 4 that approximates this function at 0, 1. Another way to state this is using our new notation, using our new language. We can say find the Maclaurin polynomial of degree 4 of our function. And that would say the same thing. By finding a Maclaurin polynomial of degree 4, we know we want a polynomial of degree 4. And we know that because it's a Maclaurin polynomial, these coefficients are all going to be found by evaluating the derivatives specifically at 0. All right? So we could either state the question this way, or we could state the question this way, and they would mean the same thing. But now let's go back and talk about a Taylor polynomial that's not centered at 0. Right? So here from our definition, we see that we have the Taylor polynomial, which can be centered at 0, and again, that's the Maclaurin polynomial. But we also have Taylor series that can be centered anywhere else, namely here at some value c. All right, so let's take a look at an example of that. Okay. So here we see the full example, so let's just go through it. The question would read something like, find the Taylor polynomial of degree 4 of f of x equals 1 over x squared at c equals to 2. I did this one ahead of time because the arithmetic is just a little annoying, and well, you didn't want to see me use a calculator over and over again, did you? So here, what this problem is saying is 1 over x squared. All right, well, there's the graph of y equals 1 over x squared. And notice that you couldn't approximate it at 0, right? A Maclaurin polynomial is nonsensical here because if you try to plug in 0 either into a function or its derivatives, those things aren't defined at 0. Okay, well, that's fine because here we're not trying for 0. We're trying to find an approximation at 2. What that means is this is the point where our approximation is centered. That's what C stands for. C stands for center. And your approximation is going to be perfect at that point, and it's going to be okay near that point. but the center is where your function should be perfect. Okay? So now, the way we find this is we're simply going to be using, up here, the definition of our Taylor series. At C, notice we're taking our function, taking its derivatives, all the way up till we reach the degree of the polynomial we want, here, nth degree polynomial, nth derivative. And once we find those derivatives, we're plugging in the center C, right there. So we go ahead and do that. F of x, f prime of x, f double prime, f triple prime, and f quadruple prime. One note here, you may or may not have seen this notation before, but if you have a derivative higher than the third derivative, you can put 4 tick marks. But another notation is the number 4 in parentheses. Without the parentheses, this means that you would take f to the 4th power. With parentheses, it means the 4th derivative of f. You can use 4 tick marks, but I mean, think about how bad that would get if you had the 40th derivative. You don't want to use 40 tick marks. So here, this is a notation that cleans that up a little bit. But you could use 4 tick marks if you like. So here are the derivatives. If that's my original function, the first derivative, I take the negative 2, bring it down, minus 1 from the power. The next one, same thing. I bring the negative 3 down. That gives me a positive 6, subtract 1 from the power. Bring the negative 4 down. That's negative 24x to the 5th power. And then for the last derivative, because I'm going to go up to the 4th derivative, that's bring the negative 5 down. That's positive 120x to the minus 6. And you know we stop at the 4th derivative because we want a 4th degree polynomial. The degree of your polynomial tells you how many derivatives you're going to need. Okay. So now once I find all those derivatives, I'm plugging in C. I'm plugging in the value of my center. So here my center is 2. So take all of these functions and plug in the number 2. So 2 to the minus 2, that's a quarter. Negative 2 times 2 to the minus third, that's negative a quarter. All I'm doing is I'm plugging in the number 2 right here. That's going to give me 6 times 2 to the minus 4, that's 3/8. Negative 24 times 2 to the minus 5, that's negative 3/4. And let's see, that's 120 times 2 to the minus 6. That's 120 over 64, which reduces to 15 over 18. This is just arithmetic. I'm just plugging the number 2 into all of those functions. But now notice that all of those numbers are just my coefficients. Oh, well, not quite. I still need to divide by something. Well, yeah, but that's not so bad. So take the coefficients that you have, your f at c, f prime at c, f double prime of c, write them all out. So here I have 1/4, negative a fourth, 3/8. I'm just using these numbers here, here, and here. Negative 3/4 goes there, and 15 over 8 goes there. But now I'm not just taking the function and its derivatives at that number. I'm also dividing by n factorial. So here, this is just going to stay the way it is. F of c stays f of c. But now the first coefficient of the first powered term gets divided by 1 factorial. The next one gets divided by 2 factorial, then 3, 4, all the way up to n. Okay, so this one stays the way it is. But that gets divided by 1 factorial, 2 factorial, 3 factorial, and 4 factorial. We know we're done because we want a 4th degree polynomial, and we've divided by n factorial at the very end. And then those are my coefficients. But of course, I still need to multiply by x minus c to the second, x minus c to the third, and so forth. So that coefficient is on its own. All right. This one is my negative 1/4 over 1 factorial times x minus c. Here, that one is the same as this one. That's going to be my f double prime over 2 factorial x minus 2 squared. Plus, and I just keep going, this is going to be my f triple prime over 3 factorial times x minus c to the third power. And finally, I have my x quadruple prime, that was this number right there, over 4 factorial times x minus 2 to the 4th power. And now I simplify the arithmetic. Here that stays negative, that stays 1/4, and dividing by 1, that also stays negative a fourth. Here, if I take 3 over 2 factorial, that's 3 over 8 over 2, that's 3/16. Here, if I divide these, 3 over 4 over 3 factorial. Well, that's going to be 1/8. Oh, there's a minus there, so that's minus 1/8. And then here, 15 over 8 over 4 factorial, that's 5 over 64. Now, I went ahead and did this on the side. I know you all know how to divide. I know how to divide as well, but sometimes the factorial freaks people out. So here, let me show you just very quickly the notation and how that simplifies to 5 over 64. If I take 15/8 over 4 factorial, okay, 15/8 over 4 factorial, that means 15/8 times 1 over 4 factorial. After all, dividing by a number is the same as multiplying by the reciprocal. And here, the reciprocal of 4 factorial over 1 is 1 over 4 factorial. But now, 4 factorial is 4 times 3 times 2 times 1. And here, I note that 3 goes into 15 5 different times. So now 1 times 5 is 5 in my numerator. And my denominator is 2 times 4 is 8, times another 8 is 64. So 5 over 64 is my coefficient over here. And that's it. This is the 4th degree Taylor polynomial of 1 over x squared equals f of x at c equals to 2. At this point, some people would now say, okay, now you're supposed to actually multiply this out, raise this to the 4th power. You're supposed to raise this to the 3rd power. You're supposed to square this. You're supposed to now distribute your coefficients and then combine all your like terms. Don't do that. If you get this far, I'm comfortable with the idea that you know what you're doing. But also, I don't want to have to grade that. I don't want to have to sit here and watch you multiply everything out like that. So here, this is how we're going to leave our answers. Could you distribute? Could you multiply these out, distribute, and combine like terms? Absolutely. But here, I'm going to ask you not to. Let's leave it that way. And finally, this brings us to the end of our section. And we'll end the section with a theorem. So this is Taylor's theorem. All right. So Taylor's theorem says, well, first of all, let's go back to Taylor's polynomial. Taylor's polynomial is an approximation. We never meant to say that this polynomial is the same as this function, right? This polynomial is not the same as this function. It's only an approximation, all right? Same thing with the one we just saw over here. I never meant to say that f of x equals 1 over x squared is the same as this polynomial. They're not. If you plug in the number 2, they're the same because that was our center. That's what we're trying to make perfect. But anything else nearby is only an approximation. Here, let's actually see what happens when you plug in 2. If you plug in the number 2, 1 over 2 squared, well, that's 1 over 4. Okay, 1/4. If you plug in 2 over here, well, that becomes 0, and that becomes 0, and that becomes 0, and that becomes 0. Okay, so you're only left with a 4th. Oh, those are the same. If you plug in c is equal to 2, these are identical. If I plug in something near to 2, they won't be identical. You can try it. I'm not going to do it. I'm not going to go through it. But you can just grab a calculator and plug in 2.1. And you'll notice that this one will give you a number. And you'll notice this one will give you a number. And they won't be exactly the same. But they'll be very, very, very close. And that's all the Taylor polynomial is. It's an approximation. It says these two may not be the same, but they're really, really close as long as you pick a number that's not too far away from that center. As long as you're not too far away from the point that we were focused on. Taylor's theorem says that we can do a lot better than that. So Taylor's theorem says the following. Let f be an n plus 1 differentiable function. Remember what that means? That means we can take the first derivative, second derivative, third derivative, all the way up to n plus 1. It's the n plus first derivative. Now let's let that function have all of those derivatives at some number c, meaning if I take all of those derivatives, at each of those derivatives, I could plug in the number c. But also, let's have that function and its n plus 1 derivatives be defined on an interval around c. Meaning, yeah, I know I can plug in c into the function and its derivatives, but I also want to be able to plug in a bunch of other numbers that are around c. Okay? So that's our situation. We have a function with n plus 1 derivatives, and I have a number and some stuff around a number, which I could plug into the function or any of its n plus 1 derivatives. All right, so that's your situation. Now, if you're in that situation, for all x in I, for every number in this interval, so here I've drawn an x for you. It doesn't have to be there. It could be on this side. It doesn't matter. For all x in this interval, there exists a number z. That z is somewhere between that center and that x. Okay, so there exists a number. What does that number do? Well, that number is such that the function is now exactly equal to its Taylor polynomial plus that little extra bit. Wait, say that again? Well, normally this and this are just an approximation. If I cover up that last term there, if I cover up that last one, this should not equal to this. This is only approximately this. A function is approximately its Taylor polynomial. But we've seen that they're not exactly the same. Here, we would use that wavy equal sign. What Taylor's theorem says is, no. The polynomial that we built is actually exactly equal to the function as long as we add a little extra something. That little extra bit will be enough to take this from almost the same to being exactly the same. Okay, so what is that extra thing we have to add? Well, it's right here. We call this Rn of x, the remainder, R for remainder, and it is. All right, normally we would just add more terms here, right? We would make this approximation have more terms by adding another term that's made up of these two factors. I would now have the next derivative over the next factorial, and that would be the next power. It would be the n plus 1 derivative of f. It would be n plus 1 factorial, and it would be x minus c to the power n plus 1. That's what my next term would normally look like. But normally, I plug in the number c. I plug in my center. What Taylor's theorem says is that somewhere near the center, some other number z, if you plug that number in, that gives you a remainder that makes that if you add that remainder to these terms, makes it exactly equal to your function. Or in other words, okay, I know the kind of term I should add, but if I add another term that's very similar, but just ever so slightly different, ever so slightly off from the center that I would normally plug in, this goes from an approximation to being exactly the right function, to being exactly equal to my function. More simply, f of x is equal to its nth degree Taylor polynomial as long as you add one more term that is just ever so slightly different from the term that you would normally add. Okay. Now, you say, well, how do I find this? How do I find that z? We're not going to worry about that. If this was a class in numerical analysis, if we were in a class of computer science, if we were trying to program a computer to do something, if we were trying to estimate values computationally, this would now take center stage. We would want to figure out what this remainder is and use it to figure out when we get an approximation that is good enough. If you think back to a previous section about alternating series, we had an example like that where we said, okay, we know that there's going to be a specific term that tells us the remainder that we would get if we subtracted the actual series from the partial series. Oh, okay, so as long as we can make that last term small enough, we're good. If this was a class in numerical analysis or if this was a class in computer science, we would now focus a lot of time on that. But this is a class in calculus, a class in theoretical analysis, which means that for us, it's sufficient to know that this number exists. And that's what the theorem says. There exists a number. In the next section, we'll see how we're going to use this to extend the Taylor polynomial from something that is an approximation. Without this is not exactly equal, it's an approximation, to something that is exactly correct, something that is exactly equal to our original function. And you'll note that in our next section, we'll be using this to confirm that fact, but we'll never actually need to figure out what that number is. So for us, Taylor's theorem is the theorem of existence. Yeah, it kind of tells you how to find the remainder. For us, all that matters is that there exists one. As long as there's one that exists, we'll be able to do what we need to do in our coming sections. So that brings us to the end of this section. Section 9.7. Here, I've written out the assignment for practice on making Taylor and Maclaurin series. Go ahead and try problems 17 through 31 odd. Section 9.7. The first half of these is making Maclaurin series, and the second half is making Taylor series at some number. Taylor series at c equal to 5 or c equals to -1 or something like that. For now, that's all that's necessary. For this section, if you know how to make a Taylor polynomial or a Maclaurin polynomial, that's all that matters. In the next section, we're going to take Taylor's theorem and use it to do a few other more impressive things. But for now, if you can make Maclaurin series and Taylor series, that brings us to the end of our section. If you have any questions, please let me know. Reach out to me, and I will answer what I can in the shortest order that I can muster. Yeah? I hope you all have a nice day.